Greek astronomy is astronomy written in the Greek language in classical antiquity. Greek astronomy is understood to include the ancient Greek, Hellenistic, Greco-Roman, and late antiquity eras. It is not limited geographically to Greece or to ethnic Greeks, as the Greek language had become the language of scholarship throughout the Hellenistic world following the conquests of Alexander. This phase of Greek astronomy is also known as Hellenistic astronomy, while the pre-Hellenistic phase is known as Classical Greek astronomy. During the Hellenistic and Roman periods, much of the Greek and non-Greek astronomers working in the Greek tradition studied at the Museum and the Library of Alexandria in Ptolemaic Egypt. The development of astronomy by the Greek and Hellenistic astronomers is considered, by historians, to be a major phase in the history of astronomy. Greek astronomy is characterized from the start by seeking a rational, physical explanation for celestial phenomena. Most of the constellations of the Northern Hemisphere derive from Greek astronomy, as are the names of many stars, asteroids, and planets. It was influenced by Egyptian and especially Babylonian astronomy. In turn, it influenced Indian, Arabic, Islamic, and Western European astronomy. Archaic Greek astronomy. References to identifiable stars and constellations appear in the writings of Homer and Hesiod, the earliest surviving examples of Greek literature. In the oldest European texts, the Iliad and the Odyssey, Homer has several astronomical phenomena including solar eclipses. Eclipses that can even permit the dating of these events as the place is known and the calculation of the time is possible, especially if other celestial phenomena are described at the same time. In the Iliad and the Odyssey, Homer refers to the following celestial objects: the constellation Boötes, the star cluster Hyades, the constellation Orion, the star cluster Pleiades, Sirius, the dog star, the constellation Ursa Major. Hesiod, who wrote in the early 7th century BC, adds the star Arcturus to this list in his poetic calendar Works and Days. Though neither Homer nor Hesiod set out to write a scientific work, they hint at a rudimentary cosmology of a flat Earth surrounded by an ocean river. Some stars rise and set, disappear into the ocean. From the viewpoint of the Greeks, others are ever visible. At certain times of the year, certain stars will rise or set at sunrise or sunset. Speculation about the cosmos was common in pre-Socratic philosophy in the 6th and 5th centuries BC. Anaximander c. 610 BC-c. 546 BC described a cyclical Earth suspended in the center of the cosmos, surrounded by rings of fire. Philolaus c. 480 BC-c. 405 BC the Pythagorean described a cosmos with the stars, planets, sun, moon, earth, and a counter-earth 10 bodies in all, circling an unseen central fire. Such reports show that Greeks of the 6th and 5th centuries BC were aware of the planets and speculated about the structure of the cosmos. Also, a more detailed description about the cosmos, stars, sun, moon and the Earth can be found in the Orphism, which dates back to the end of the 5th century BC, and it is probably even older. Within the lyrics of the Orphic poems we can find remarkable information such as that the Earth is round, it has an axis and it moves around it in one day, it has 3 climate zones and that the Sun magnetizes the stars and planets. The planets in early Greek astronomy. The name, planet, comes from the Greek term planet, meaning wanderer, as ancient astronomers noted how certain lights moved across the sky in relation to the other stars. 5 planets can be seen with the naked eye: Mercury, Venus, Mars, Jupiter, and Saturn, the Greek names being Hermes, Aphrodite, Ares, Zeus and Cronus. Sometimes the luminaries, the Sun and Moon, are added to the list of naked eye planets to make a total of 7. Since the planets disappear from time to time when they approach the Sun, careful attention is required to identify all 5. Observations of Venus are not straightforward. Early Greeks thought that the evening and morning appearances of Venus represented 2 different objects, calling it Hesperus, evening star, when it appeared in the western evening sky, and Phosphorus, light bringer, when it appeared in the eastern morning sky. They eventually came to recognize that both objects were the same planet. Pythagoras is given credit for this realization. Eudoxan astronomy. In classical Greece, astronomy was a branch of mathematics. Astronomers sought to create geometrical models that could imitate the appearances of celestial motions. This tradition began with the Pythagoreans, who placed astronomy among the four mathematical arts along with arithmetic, geometry, and music. The study of number comprising the four arts was later called the quadrivium. Although he was not a creative mathematician, Plato 427 to 347 BC included the quadrivium as the basis for philosophical education in the Republic. He encouraged a younger mathematician, Eudoxus of Cnidus c. 410 BC. 347 BC, to develop a system of Greek astronomy. According to a modern historian of science, David Lindberg, in their work we find 1 a shift from stellar to planetary concerns, 2 the creation of a geometrical model, the two-sphere model, for the representation of stellar and planetary phenomena, and 3 the establishment of criteria governing theories designed to account for planetary observations. The two-sphere model is a geocentric model that divides the cosmos into two regions, a spherical Earth, central and motionless, the sublunary sphere, and a spherical heavenly realm centered on the Earth, which may contain multiple rotating spheres made of ether. Plato's main books on cosmology are the Timaeus and the Republic. In them he described the two-sphere model and said there were 8 circles or spheres carrying the 7 planets and the fixed stars. According to the myth of in the Republic, the cosmos is the spindle of necessity, attended by sirens and spun by the 3 daughters of the goddess Necessity known collectively as the Moirai or Fates. According to a story reported by Simplicius of Cilicia 6th century, Plato posed a question for the Greek mathematicians of his day. By the assumption of what uniform and orderly motions can the apparent motions of the planets be accounted for? Quoted in Lloyd 1970, p. 84. Plato proposed that the seemingly chaotic wandering motions of the planets could be explained by combinations of uniform circular motions centered on a spherical Earth, apparently a novel idea in the 4th century. Eudoxus rose to the challenge by assigning to each planet a set of concentric spheres. By tilting the axes of the spheres, and by assigning each a different period of revolution, he was able to approximate the celestial appearances. Thus, he was the first to attempt a mathematical description of the motions of the planets. A general idea of the content of On Speeds, his book on the planets, can be gleaned from Aristotle's Metaphysics 12:8, and a commentary by Simplicius on De Caelo, another work by Aristotle. Since all his own works are lost, our knowledge of Eudoxus is obtained from secondary sources. Aratus's poem on astronomy is based on a work of Eudoxus, and possibly also Theodosius of Bithynia's Sphaerix. They give us an indication of his work in spherical astronomy as well as planetary motions. Callippus, a Greek astronomer of the 4th century, added 7 spheres to Eudoxus' original 27. In addition to the planetary spheres, Eudoxus included a sphere for the fixed stars. Aristotle described both systems, but insisted on adding unrolling spheres between each set of spheres to cancel the motions of the outer set. Aristotle was concerned about the physical nature of the system. Without unrollers, the outer motions would be transferred to the inner planets. Topic: Hellenistic astronomy. Topic: Planetary models and observational astronomy. The Eudoxian system had several critical flaws. One was its inability to predict motions exactly. Callippus' work may have been an attempt to correct this flaw. A related problem is the inability of his models to explain why planets appear to change speed. A third flaw is its inability to explain changes in the brightness of planets as seen from Earth. Because the spheres are concentric, planets will always remain at the same distance from Earth. This problem was pointed out in antiquity by Autolycus of Pitane c. 310 BC. Apollonius of Perga c. 262 BC. 190 BC responded by introducing 2 new mechanisms that allowed a planet to vary its distance and speed, the eccentric deferent and the deferent and epicycle. The deferent is a circle carrying the planet around the Earth. The word deferent comes from the Greek phero, to carry, and Latin fero, fere, meaning to carry. An eccentric deferent is slightly off-center from Earth. In a deferent and epicycle model, the deferent carries a small circle, the epicycle, which carries the planet. The deferent and epicycle model can mimic the eccentric model, as shown by Apollonius' theorem. It can also explain retrogradation, which happens when planets appear to reverse their motion through the zodiac for a short time. Modern historians of astronomy have determined that Eudoxus' models could only have approximated retrogradation crudely for some planets, and not at all for others. In the 2nd century BC, Hipparchus, aware of the extraordinary accuracy with which Babylonian astronomers could predict the planets' motions, insisted that Greek astronomers achieve similar levels of accuracy. Somehow he had access to Babylonian observations or predictions, and used them to create better geometrical models. For the Sun, he used a simple eccentric model, based on observations of the equinoxes, which explained both changes in the speed of the Sun and differences in the lengths of the seasons. For the Moon, he used a deferent and epicycle model. He could not create accurate models for the remaining planets, and criticized other Greek astronomers for creating inaccurate models. Hipparchus also compiled a star catalogue. According to Pliny the Elder, he observed a nova, new star. So that later generations could tell whether other stars came to be, perished, moved, or changed in brightness, he recorded the position and brightness of the stars. Ptolemy mentioned the catalogue in connection with Hipparchus' discovery of precession. Precession of the equinoxes is a slow motion of the place of the equinoxes through the zodiac, caused by the shifting of the Earth's axis. Hipparchus thought it was caused by the motion of the sphere of fixed stars. Heliocentrism and cosmic scales. In the 3rd century BC, Aristarchus of Samos proposed an alternate cosmology, arrangement of the universe, a heliocentric model of the solar system, placing the Sun, not the Earth, at the center of the known universe, hence he is sometimes known as the Greek Copernicus. His astronomical ideas were not well received, however, and only a few brief references to them are preserved. We know the name of one follower of Aristarchus, Seleucus of Seleucia. Aristarchus also wrote a book on the sizes and distances of the Sun and Moon, which is his only work to have survived. In this work, he calculated the sizes of the Sun and Moon, as well as their distances from the Earth in Earth radii. Shortly afterwards, Eratosthenes calculated the size of the Earth, providing a value for the Earth radii which could be plugged into Aristarchus' calculations. Hipparchus wrote another book on the sizes and distances of the Sun and Moon, which has not survived. Both Aristarchus and Hipparchus drastically underestimated the distance of the Sun from the Earth. Astronomy in the Greco-Roman and late antique eras. Hipparchus is considered to have been among the most important Greek astronomers, because he introduced the concept of exact prediction into astronomy. He was also the last innovative astronomer before Claudius Ptolemy, a mathematician who worked at Alexandria in Roman Egypt in the 2nd century. Ptolemy works on astronomy and astrology include the Almagest, the planetary hypotheses, and the Tetrabiblos, as well as the Handy Tables, the Canobic inscription, and other minor works. Ptolemaic astronomy. The Almagest is one of the most influential books in the history of Western astronomy. In this book, Ptolemy explained how to predict the behavior of the planets, as Hipparchus could not, with the introduction of a new mathematical tool, the equant. The Almagest gave a comprehensive treatment of astronomy, incorporating theorems, models, and observations from many previous mathematicians. This fact may explain its survival, in contrast to more specialized works that were neglected and lost. Ptolemy placed the planets in the order that would remain standard until it was displaced by the heliocentric system and the Tychonic system. Moon, Mercury, Venus, Sun, Mars, Jupiter, Saturn. Fixed stars. The extent of Ptolemy's reliance on the work of other mathematicians, in particular his use of Hipparchus' star catalogue, has been debated since the 19th century. A controversial claim was made by Robert R. Newton in the 1970s. In The Crime of Claudius Ptolemy, he argued that Ptolemy faked his observations and falsely claimed the catalogue of Hipparchus as his own work. Newton's theories have not been adopted by most historians of astronomy. A few mathematicians of late antiquity wrote commentaries on the Almagest, including Pappus of Alexandria as well as Theon of Alexandria and his daughter Hypatia. Ptolemaic astronomy became standard in medieval Western European and Islamic astronomy until it was displaced by Marian, heliocentric and Tychonic systems by the 16th century. However, recently discovered manuscripts reveal that Greek astrologers of antiquity continued using pre-Ptolemaic methods for their calculations. AABOE, 2001. Influence on Indian astronomy. Hellenistic astronomy is known to have been practiced near India in the Greco-Bactrian city of Ai-Khanoum from the 3rd century BC. Various sundials, including an equatorial sundial adjusted to the latitude of Ujjain, have been found in archaeological excavations there. Numerous interactions with the Mauryan Empire, and the later expansion of the Indo-Greeks into India suggest that some transmission may have happened during that period. Several Greco-Roman astrological treatises are also known to have been imported into India during the first few centuries of our era. The Yavanajataka, sayings of the Greeks, was translated from Greek to Sanskrit by Yavanesvara during the 2nd century, under the patronage of the western satrap Saka king Rudradaman I. Rudradaman's capital at Ujjain became the Greenwich of Indian astronomers and the Arin of the Arabic and Latin astronomical treatises, for it was he and his successors who encouraged the introduction of Greek horoscopy and astronomy into India. Later in the 6th century, the Romaka Siddhanta, doctrine of the Romans, and the Paulisa Siddhanta, sometimes attributed as the doctrine of Paul, or in general the doctrine of Paulisa Muni, were considered as two of the 5 main astrological treatises, which were compiled by Varahamihira in his Pansa Siddhantika, 5 treatises. Varahamihira wrote in the Brihat Samhita, "For, the Greeks are foreigners. This science is well established among them. Although they are revered as sages, how much more so as a twice-born person who knows the astral science." Sources for Greek astronomy. Many Greek astronomical texts are known only by name, and perhaps by a description or quotations. Some elementary works have survived because they were largely non-mathematical and suitable for use in schools. Books in this class include the Phenomena of Euclid and 2 works by Autolycus of Pitane. 3 important textbooks, written shortly before Ptolemy time, were written by Cleomedes, Geminus, and Theon of Smyrna. Books by Roman authors like Pliny the Elder and Vitruvius contain some information on Greek astronomy. The most important primary source is the Almagest, since Ptolemy refers to the work of many of his predecessors. Evans 1998, p. 24. Famous astronomers of antiquity. In addition to the authors named in the article, the following list of people who worked on mathematical astronomy or cosmology may be of interest. Anaxagoras, Archimedes, Archytas, Aristaeus, Aristarchus, Aristillus, Conon of Samos, Democritus, Empedocles, Heraclides Ponticus, Hicetas, Hippocrates of Chios, Macrobius, Martianus Capella, Menelaus of Alexandria, Menelaus theorem, Meton of Athens, Parmenides, Porphyry, Posidonius, Proclus, Thales, Theodosius of Bithynia. See also: AntiKythera mechanism, Greek mathematics, History of astronomy, Babylonian influence on Greek astronomy. Notes. References. AABOE, Asghar H. 2001. Episodes from the Early History of Astronomy. New York, Springer. ISBN 978-0-387-95136-2. Dreyer, John L. E. 1953. A History of Astronomy from Thales to Kepler, 2nd ed. New York, Dover Publications. ISBN 978-0-486-60079-6. Evans, James. 1998. The History and Practice of Ancient Astronomy. New York, Oxford University Press. ISBN 978-0-19-509539-5. Heath, Thomas L. 1913. Aristarchus of Samos. Oxford, Clarendon Press. Lindbergh, David C. 2010. The Beginnings of Western Science, The European Scientific Tradition in Philosophical, Religious, and Institutional Context, 600 BC to AD 1450 2 ed. Chicago, University of Chicago Press. ISBN 978-0-226-48204-0. Lloyd, Geoffrey E. R. 1970. Early Greek Science, Thales to Aristotle. New York, W. W. Norton & Co. Neugebauer, Otto E. 1975. A History of Ancient Mathematical Astronomy. Berlin, Springer. ISBN 978-0-387-06995-1. Newton, Robert R. 1977. The Crime of Claudius Ptolemy. Baltimore, Johns Hopkins University Press. ISBN 978-0-8018-1990-2. Peterson, Olaf 1993. Early Physics and Astronomy, A Historical Introduction 2nd ed. Cambridge, Cambridge University Press. ISBN 978-0-521-40340-5. Revello, Manuela 2013. Sol, Luna ed Ecclesi in Omero, in Technai 4. Pisa Roma, Fabrizio Serra Editore. pp. 13–32. Toomer, Gerald J. 1998. Ptolemy Almagest. Princeton, Princeton University Press. ISBN 978-0-691-00260-6. External links. Almagest Planetary Model Animations. MacTutor History of Mathematics Archive